Hi everyone, this is Becky, and in this video we are going to talk about bonding models. Okay, so our goal of this video is to relate electron arrangements within a substance to the observable properties of that substance. So thinking about how the types of bonds that are formed between elements influences the macroscopic properties of the compound. So macroscopic being the properties that we can see and measure. Okay. So just a quick review from what we were working on in class. Remember that a bond, chemical bond, it's formed by two valence electrons, right? We're talking about electrostatic interactions involving attractions and repulsions between atoms and valence electrons. Okay, and that the type of bond that forms between two atoms really depends on and is influenced by and really depends on the idea of the difference in electronegativity between the two elements in the compound or in the bond, right? And it's that difference in electronegativity that determines the type of bond, and then the type of bond actually has a huge influence on both physical and chemical properties. This video we're going to consider physical. We'll think about chemical properties later. Okay, so remember that electronegativity is the affinity of an atom for shared electrons, essentially the ability of an atom to attract bonding electrons to itself, right? So if I have a bond here that I'm forming between element X and element Y, and remember that that's two valence electrons, the pull from X on those valence electrons is its electronegativity, and the pull from Y is its electronegativity. Remember that because noble gases don't typically bond, noble gases don't typically have electronegativity values, and that electronegativity values increase as we get closer towards fluorine. So fluorine is the most electronegative element on the table. Something like francium or cesium are the least electronegative. Nonmetals have higher electronegativity than metals do. And hydrogen has an electronegativity roughly equal to that of carbon in terms of its scale. Hydrogen's a nonmetal. Remember, we put it there because it's got one valence electron, but it's dumb. It shouldn't be there. It doesn't match, and this is one of the ways where it doesn't match. Its electronegativity is closer to that of carbon. Okay, so if the electronegativity is what determines is the affinity or the ability of an atom to attract bonding electrons, it's not the it's not the electronegativity itself that determines the type of bond, but rather is the difference in electronegativity that matters for determining the type of bond. And now you've heard the terms ionic and covalent before, and I want to just really emphasize and draw your attention to the fact that this is a continuum. This is a spectrum. This is not there is a defined ionic, and it's not like there's not a clear line here. There's not a clear break. It's a spectrum of things. And we're looking at the difference. So we're looking at the difference in electronegativity here. And typically we're going to draw this line for determining the difference between ionic bonds and covalent bonds as here, somewhere in the middle, right here, around 2. And we're going to call that difference about 2. And if the difference in electronegativity is greater than 2, we're going to call it an ionic bond. And if it's less than 2, we're going to call it a covalent bond. Now, remember that for an ionic bond, the difference in electronegativity is so great that those electrons end up on the more electronegative element, and I have a positive ion, an ion that has lost an electron, and a negative ion, an ion that has gained an electron, kind of held together by electrostatic charge. So remember that this thing that holds these together is the fact that opposite charges attract. So we're looking at opposite charge attraction between the positive ion and the negative ion. And if the difference in electronegativity is less than that, then we're talking about, okay, so these electrons are now shared, right? So in a covalent bond, electrons are shared. They could be shared evenly, which is what happens when you have a low difference in electronegativity. When you have kind of a medium difference in electronegativity, they're shared, but they're not shared equally. So you end up with partial positive and partial negative charges, but we'll talk about that later. For right now, what we want to think about is the idea of a covalent bond where these electrons are shared equally between those two elements, and this creates this small stable unit where this small unit X and Y are held together. The only thing that holds X and Y together in an ionic bond is the difference in charge. Okay, So that being said, let's take a look at the differences in compounds that are formed or compounds that exist between if you have a substance that is held together via ionic bonds versus covalent bonds. Then we'll talk about a weird one that explains the properties of metals. So ionic bonding for compounds that are held together by ionic bonds. Think about things like NaCl, so sodium chloride, calcium fluoride, etc. What we're looking at here for these things is we're looking at a metal and a non-metal. That's what makes something an ionic, like typically ionic bond. So we're talking about a big difference in electronegativity. So what we have here is the valence electron is on the non-metal atom. It's on the atom with more electronegativity. So we end up with this series of negative ions. So you see these clouds, this gray stuff, this gray cloud here represents the valence electrons. So they're alternating. So positive, negative, positive, negative. So you see where you have negative ions next to positive ions to minimize electrostatic repulsion and maximize electrostatic attraction, right? So remember that what you have is a series of ions that are held together because opposite charges attract. So held they're held together because of opposite charge attraction. What this means, and remember that opposite charge attraction is a strong force. So what that means is that ionic compounds are solids. Oops, sorry guys. These are solids. They are solids at room temperature. They tend to have high melting points and boiling points. They tend to be brittle. And they do some other really cool, fun things that we'll talk about next week. Okay, covalent compounds are something like CO2, H2O, CF4, HOCl. So here we're talking about things that form between nonmetals. So if you have two or more nonmetals, what you typically have is a covalent compound. And remember that with covalent compounds, those valence electrons are shared. And so you end up with this here where you have these very strong covalent bonds within a unit, and then these relatively weak kind of nothing there between units, right? So within a unit, you have this really strong force that holds the unit together, and then between units, there's not a strong force. And so you end up with this small stable unit within the structure. And so this small stable unit is what I'm circling in red. And that small stable unit is what we call a molecule. All right, so we have a molecule. And those molecules are held to other molecules by not covalent bonds, by weak, what we call intermolecular forces. Okay, and the cool thing about covalent compounds is that the properties of this molecule depend entirely on how those atoms are arranged. So the properties depend on the structure of the compound, which depend on what's there and how those things are connected, which is kind of cool because covalent compounds can have vastly different properties from each other. This is the type of bond substance that has the most varied properties. These can be solids, liquids, and gases at room temperature. They tend to have relatively low melting and boiling points, but you could also get covalent compounds that actually have pretty high melting and boiling points. Some of them dissolve in water, some of them don't. It's very, very varied because the properties of those really, really, really only depend on the structure. They depend on the structure. And there are so many different possible structures that it's impossible to really kind of quantify it beyond that. Okay. Notice that there is a distinction here between the ionic compounds. So if I have an ionic compound here, the force here, this force is the same as this force is the same as this force. Ionic compounds don't form molecules, right? But they don't form a small stable unit because all of the forces are kind of equal. There's no force that's stronger than others. So they don't form that small stable unit. Just an important thing to note that I want to make sure that you're aware of. Okay, recap. The types of bonds that are present within a substance influence the physical properties of that substance. They also influence the chemical properties, but right now we're thinking about physical properties. And that they result in different arrangements of atoms. So if I have something that is ionic, what I have is a sea of negative ions and positive ions, negative, positive, so this alternating crystalline arrangement of ions that results in a brittle, high melting point structure. If that's a covalent compound, I have these small stable units that are called molecules. So the molecules are held together by covalent bonds, and then the molecules are held to other molecules by relatively weak forces. I hope that you wrote down some questions. This is not easy to grasp the first time. So write down your questions, bring your questions to class, and we'll see you next time.